Welcome, gentle traveler, to this quiet space we are creating together. A sanctuary built not of stone or wood, but of thought and whispered wonder. Take a soft breath now. Feel the gentle rise and fall within you. Where are you in this moment? What time is it for you? Perhaps the stars are beginning to speckle the sky, or maybe the first blush of dawn is painting the horizon, or it might be the deep, quiet dark of midnight, holding the world in its hushed embrace. Whatever time it is, wherever you are welcome here. There is no urgency in this space. No need to rush, no answers to chase. We are simply going to drift, to explore, to allow our minds to wander through concepts so vast, so profound, that they invite not the hurried quest for solutions, but a deep, comforting stillness. This is not a lecture, nor is it a search for medical advice or quick fixes. This is an invitation to simply be, to let curiosity be your soft companion, and to find a gentle peace in the very act of pondering the immense. Beautiful mysteries that surround us, and indeed, lie within us. Our journey begins not with a bang, but with a whisper, echoing from a time when our understanding of the universe was itself just a fragile seedling. Peeking through a dense fog, imagine, if you will, the early 19th century, an amateur cartographer named Edward Quinn, with meticulous dedication, spent years crafting his masterpiece, a book he called the Historical Atlas, published in 1830, just 2 short years after his passing. This atlas was more than just a collection of maps. It was a visual poem, a testament to how humanity's knowledge of the world gradually emerged from the shadows of ignorance. Quinn depicted our understanding as a flickering light, steadily blowing away clouds of unknowing, unveiling continents and civilizations that had long been shrouded in mystery. His atlas began with a map drawn from the narratives of the Bible, showing a known world that was little more than the fertile crescent of the Euphrates and Tigris rivers. For those ancient peoples, this small patch of land was their entire world, surrounded by a vast, uncharted darkness, a fog of the unknown that stretched to every horizon. As you turn the pages of Quinn's atlas, time gently marches on, and with each passing epoch, more of the world is revealed. We journey through the biblical exodus of the Israelites, a story of movement and discovery, where new lands, new possibilities, slowly came into view. Then, the coming of the mighty Roman Empire, its legions pushing outward, extending their reach, and in doing so, dispersing more of those geographical clouds, unveiling new territories, new peoples, bringing them into the realm of the known. By the early 19th century, the pages of Quinn's atlas show the clouds almost fully dispersed. All the major continents, as understood by European explorers, are visible, it might have seemed, to those peering at his detailed maps. That there was no more land left to discover, no more geographical mysteries to solve. The world, in their eyes, was finally laid bare, charted, and understood. This perspective, of course, was deeply rooted in a European viewpoint. For an artist in ancient China, their own historical atlas would begin with their central kingdom, surrounded by its own unique darkness, its own specific barbarian lands, shrouded in mystery. In India, in the vast plains of Australia, or across the vibrant lands of the Americas, each culture would have their own origin story, their own small portion of the world, surrounded by their own particular clouds of unknowing. The focus, the center, the very shape of the known would be entirely different. And indeed, these clouds were not solely geographical. This metaphor, this gentle idea of a clearing fog, extends far beyond the physical landscape of Earth. All human endeavors, every new field of study, every great quest for understanding, begins shrouded in a similar fog of mystery. This fog only begins to clear, only begins to thin, when we learn something new, when we gain a fresh insight, when a piece of the puzzle finally clicks into place, like the once sheathed surface of the Earth, slowly revealing its intricate contours. Clouds of mystery have also, for eons, shrouded the very universe itself, for much of human history. The heavens above were the ultimate mystery. The stars were distant, unchanging points of light, their nature unknown, their distances unfathomable. The planets were wandering lights, their movements observed with reverence and superstition, but their true composition and orbits were veiled. The vastness beyond our immediate world was the deepest, most impenetrable fog of all, a realm reserved for gods and myths. Yet, over the last few hundred years, a quiet, persistent curiosity began to turn our attention, and our instruments, to these celestial realms. With the invention of the telescope, a revolutionary tool that extended our natural sight, we began to peer deeper and deeper into the cosmic unknown. Our initial glimpses were modest, revealing mountains on the moon, moons around Jupiter, and the rings of Saturn. But with each refinement, each more powerful lens, our vision extended further, piercing through layers of cosmic fog. We began to spy individual stars, not just as points of light, but as distant suns. Then came the realization that these stars were gathered into immense collections, galaxies, vast island universes of their own. Our telescopes grew more powerful, allowing us to distinguish these galaxies, to see their spiral arms, their elliptical shapes, their incredible variety. We learned that our own Milky Way was just one among billions, perhaps trillions. We have now peered back over 13 billion years, using the faint, ubiquitous glow of the cosmic microwave background radiation, the very afterglow of creation itself. This ancient light, stretched and cooled by the universe's expansion, is a direct echo of the universe when it was a mere infant. Just 380,000 years old, it is the furthest back in time we can see. A shimmering, ancient portrait of the early cosmos, a testament to how far the clouds of ignorance about our origins have dispersed. It is like seeing the first hazy photograph of a newborn universe, warm and dense, and remarkably, our understanding has grown so profound that we can even deduce the future history of our universe. Looking to days unimaginably far off, we can project forward, through trillions of years, to the time of the last star, when even the longest lived, faintest red dwarfs will have finally flickered out, leaving behind only cold, dark remnants. We can look even further into our inevitable future, to the time when matter itself might subtly melt away, and even the most massive black holes, those cosmic behemoths, slowly evaporate over timescales that defy comprehension, leaving behind only the faintest whispers of radiation. One by one, the universe has quietly, patiently given up its secrets, revealing its past, its present, and its far-flung future. The cosmic clouds have steadily been lifted, revealing a grand, intricate tapestry of time. Looking at this incredible progress, it might, for a moment, appear that we have learned all there is to learn about the cosmos, that the map is complete, the clouds fully dispersed. This is a tempting thought, a comforting sense of having arrived at the final frontier of knowledge. But history, with its gentle, persistent lessons, offers a wise caution. Consider the renowned American astronomer and mathematician, Simon Newcomb. In 1888, he confidently claimed that we had reached the limits of astronomy, suggesting that there was little left to discover yet. He passed away in 1909, just as Albert Einstein was upending the entire world of physics with his revolutionary theories of relativity, completely reshaping our understanding of space, time, and gravity. Newcomb's fate serves as a subtle, powerful reminder it is always a bad idea to bet against further discoveries. to assume the book of knowledge is closed. And so, this is where scientists find themselves now. In this very moment, they stand tall, not on solid ground, but on towering structures of complex equations, elaborate theories, and remarkable observational tools. With these sophisticated instruments, both physical and conceptual, they try to peer even further into the lingering cosmic fog. They ask questions that push the very boundaries of our current understanding. Questions that echo in the vast silence between the stars. But unlike Quinn's atlas, where the clouds were purely a fog of distance, hiding lands far away, the current clouds of cosmic mystery are different. These are clouds that linger not just far away, but subtly around us, intimately within us, and surprisingly, even before us. These are not merely geographical barriers to exploration. They are fundamental enigmas woven into the fabric of reality itself. These are new universes, potentially born beyond our current cosmic horizon, forever out of our direct sight. These are secrets hidden in our distant cosmic past, perhaps even before the Big Bang as we understand it, and most mind-bendingly, these are new possibilities, new realities, perhaps even new universes, born even inside us with every fleeting instance that passes. With every quantum choice made, the fog has become far more complex, far more intriguing, encompassing not just space, but time, and even the very nature of existence. As our knowledge of theoretical physics has grown, what had once seemed radical, bordering on the fantastical, has gradually, almost gently, forced its way into the realm of possibility, and then, perhaps even probability. Ideas that were once dismissed as science fiction now lie at the heart of serious scientific inquiry. Multiverse theories, once confined to the fringes of speculation, have proliferated, each hoping to answer some of the deepest, most profound questions about what we are and what the entire cosmos truly is. From the mind-boggling notion of parallel worlds filled with infinite versions of you, living out every conceivable permutation of your life, to barren deserts of endless nothingness, where no stars ever form and no life ever stirs, scientists are diligently blowing away this new cosmic fog of unknowing. They are revealing a warped, intricate Russian doll of infinities, nested both subtly within and vastingly right next to each other. It's a vision that expands our sense of reality beyond anything Quinn could have ever imagined. A quiet revolution in our understanding of what everything truly means. Welcome, gentle explorer, to this new unfolding of our journey into the cosmic unknown. Take another soft, settling breath now. Feel the quiet hum of existence around you as we delve into the wondrous concept of multiverses. Remember that this is a space for gentle curiosity, not for strenuous intellectual heavy lifting. Let your mind float, like a feather on a soft breeze. Through these vast, intriguing ideas, there is no need to grasp every detail, only to allow the profound implications to wash over you, bringing a sense of spaciousness and quiet wonder. Imagine, if you will, the simple yet profound definition we will use for our purposes here. Let's call something like our observable universe, the one we can see with our most powerful telescopes. Simply a universe. It's the bubble of reality from which light has had enough time to reach us since the Big Bang. Now, if we accept what our cosmic equations are gently whispering to us, then beyond the farthest reaches of this observable bubble, there are countless other universes. These aren't just empty spaces, they are full-fledged universes, potentially rich in stars, galaxies, and perhaps even life, just like our own. This grand collection, this unimaginably vast assembly of individual universes, is what we call the first level of the multiverse. The physicist Max Tegmark, a gentle guide in these complex realms, refers to this as a level 1 multiverse. It's a concept that grows naturally from the simplest picture of our universe, an infinite expanse of space. Let's explore this level 1 multiverse with a soft, open mind, as we mentioned. In this particular vision of the multiverse, beyond our cosmic horizon, there is possibly an infinite number of other universes. Each one, in its general character, it is much like our own. They were all born around 13.8 billion years ago, from a similar kind of Big Bang, and they contain similar proportions of stars and galaxies. And, tantalizingly, they hold the potential for life, just as our own universe does. However, if we follow the gentle logic of infinity and allow our minds to wander just a little further, a truly remarkable, even a touch disturbing, picture begins to softly emerge. In our level 1 multiverse, each individual universe is roughly the same size, each containing a roughly similar number of atoms arranged into planets, stars, and galaxies. But the sheer, boundless nature of infinity means that anything that can happen must happen. Somewhere, out there, in the quiet, endless void. Some of these universes will be not just similar, but absolutely and precisely identical to ours. Imagine this with a sense of calm wonder in one of these other universes. There will be a Milky Way galaxy, an exact replica of the one we inhabit. Within that galaxy, there will be a star identical to our Sun, glowing with the same steady warmth, and orbiting that star, there will be a planet, precisely identical to Earth, with its vast oceans, its winding continents, its whispering plants, and its countless diverse animals. And of course, on that identical Earth, there will be people. Everyone you know, every face you recognize, every voice you cherish. They are all there, living out their copies of their lives, playing out the very same moments, the very same decisions. And to stretch your mind just a little further, there will be another version of you in that very universe, watching this exact moment unfold, reading these very words, experiencing this same gentle contemplation. Such a situation, while profoundly intriguing, would be vanishingly rare. Most universes in this infinite expanse would be only roughly similar to our own, perhaps with a slightly different arrangement of stars, a different history, a subtle change in events. But here's the key. The quiet paradox of infinity, a vanishingly rare percentage of an infinite number, is still itself an infinite number. So, there are not just one or two, but an infinite number of these identical copies. These doppelgangers of our universe and of you. How far away might such an identical copy of you be? Max Tegmark, with his keen insights, estimates a distance almost beyond imagining something like 10 to the power of 118 meters. To put that into a soft perspective, our own observable universe, the one we can see, has a diameter of roughly 10 to the power of 27 meters. So, this identical copy is vastly, almost incomprehensibly, further away than anything we could ever hope to see. And, importantly, they are causally disconnected. This means that no light rays, no signals of any kind, can ever be exchanged between our universe and theirs. They are beyond each other's cosmic horizons, destined to be forever separate, utterly unaware of each other's existence. But they would be out there, nonetheless, in the infinite, along with every possible variation, every subtle permutation of reality you could ever imagine. The quiet implication here is profound. Anything that has even the slightest chance of happening, no matter how improbable, must happen somewhere in this infinite level 1 multiverse. Every choice you didn't make, every path not taken, every what-if scenario you've ever pondered is playing out in countless other realities. And yet, despite this mind-bending infinity, we are forever locked within our own observational universe. We are eternally bound to see nothing but our tiny patch, our familiar bubble of reality. The infinite parallel worlds of the level 1 multiverse are lost to us. hidden behind our cosmic horizon, forever beyond our direct interaction. It's a comforting thought. Perhaps that we don't have to contend with all those infinite versions of ourselves and our choices. Only the one unfolding here, now. This, however, is just the beginning. This is merely level 1. Just one mind-melting deduction, gently drawn from our current understanding of the laws of physics, as we prepare to take another step up Max Tegmark's ladder of multiverses. Our picture of the cosmos is about to become even stranger, even more wonderfully complex. Let's begin to ponder the next grand question, one that touches upon the very fabric of our existence. Why does our universe have its particular, precise laws of physics? This might seem like a strange question at first. How could it have been otherwise? How could gravity behave differently? How could electrons have a different charge? These laws seem so fundamental, so unyielding, so intrinsic to reality. But as our knowledge of the workings of space and time has advanced steadily across the 20th century, it has become harder and harder to ignore a remarkable, even baffling, cosmic phenomenon. The universe appears finely tuned for life. In the 1960s, a visionary cosmologist named Robert Dicke gently suggested that the fundamental forces of gravity and electromagnetism seemed to be incredibly finely balanced. His quiet thought was this: if these forces were not precisely tuned to their current strength, stars simply would not shine as they do, or perhaps not at all, and life as we know it, dependent on the stable energy of stars, would be impossible. As physicists continued to stare deeply into their complex equations, more and more examples of this exquisite fine-tuning began to reveal themselves, like hidden patterns emerging from a vast tapestry. The esteemed astronomer Fred Hoyle, with his profound understanding of stellar alchemy, found that even tiny, subtle changes in the strong nuclear forces, the very glue that binds atomic nuclei, would result in a universe utterly devoid of carbon. Carbon, as we know, is the very backbone of life, the versatile element that allows for complex organic molecules. Without it, the chemistry of life would be impossible. Then, the brilliant physicist Steven Weinberg noted a similar, startling sensitivity: a universe with even slightly more dark energy, that mysterious repulsive force we've discussed, would expand too rapidly, too violently, for stars or galaxies to ever have the chance to form. Without stable stars, there is no place for planets, no source of long-term energy, no opportunity for life. Serendipity seemed to pile on top of serendipity, a cascade of improbable coincidences. It became profoundly apparent that if our universe were even very slightly different in its fundamental parameters, we simply would not exist. Our cosmos appeared to have just the right physics, a delicate, almost miraculous calibration, to allow for the immense complexity of life to emerge and flourish. And it is in that key adjective, that quiet emphasis, our cosmos, that the gentle answer, or at least a powerful hint towards it, may lie. This apparent fine-tuning, this astonishing suitability of our universe for life, is the very problem through which we can take our first ethereal steps into the Level 2 multiverse, though there is more than one way to construct a Level 2 multiverse, a concept where not just space, but the very laws of physics can vary. We will begin our contemplation with the most widely discussed idea: inflation. Imagine inflation as a burst of incredibly rapid, almost unimaginable, universal expansion that occurred in the earliest moments of our cosmos, fractions of a second after its birth, when inflation was originally proposed by the visionary physicist Alan Guth. The idea was that this immense expansion turned on and off in an unbelievably tiny window of time, a trillionth of a trillionth of a trillionth of a second. Its purpose was elegant and profound. It smoothed out the universe, making it incredibly uniform on large scales, and it simultaneously seeded the tiny quantum fluctuations that would later grow. through the patient pull of gravity, into the large-scale structure of galaxies we observe today. It seemed like an essential ingredient for explaining the remarkably homogeneous and flat universe around us. An almost perfect solution, but immediately, a subtle problem emerged, one that gently threatened the very heart of the idea itself. How could this incredible burst of inflation be synchronized, turning on and off uniformly, across the entire cosmos within that infinitesimally tiny window of time? The calculations, when gently prodded, suggested that the end of inflation would be incredibly messy, far from the neat, synchronized picture initially imagined, whilst in some places, inflation would indeed come to an end after a short burst, gracefully handing over to the slower, familiar expansion we see today. In other regions, inflation would simply continue, relentlessly pushing space apart. This lack of a graceful, universal exit for inflation appeared, for a while, to spell doom for the beautiful theory. However, the idea of inflation was too attractive, too powerful in its explanatory potential. To simply abandon, it held the key to so many puzzles. And so, by the 1980s, a flurry of intense intellectual activity gave birth to a new theory of inflation, a revised and more robust version that embraced the very messiness that had initially seemed problematic. The key architects of this refreshed vision were brilliant minds like Andre Lin, Andreas Albrecht, and Paul Steinhardt. It was this second wave of thought that introduced a now essential, almost poetic, part of the idea, the inflaton. Imagine the inflaton as a pervasive, invisible field, a subtle sea of energy that permeated the entire early universe. It was this field, with its unique properties, that provided the immense impetus, the gentle but unstoppable push. For inflation, crucially, this new theory of inflation fully embraced the very messiness of the original idea. As the cosmos inflates, instead of inflation ending everywhere at once, individual universes continually, gently crystallize out of the ongoing inflation. Picture it like this. Imagine an endlessly expanding cosmic foam, and within this foam, bubbles are constantly forming, detaching, and then expanding on their own. Each of these bubbles is a distinct universe. In this picture, inflation never truly ceases. It continues for eternity, an unending cosmic engine. And as it does, more and more universes, more and more bubbles of reality, crystallize out, each embarking on its own unique journey of expansion and evolution. Within this eternal inflation, our level 1 infinite multiverse, that vast collection of causally disconnected identical and near-identical copies of our universe, is just one of countless many. These various level 1 multiverses are separated from each other by ever-inflating, immense stretches of space and time, making them fundamentally beyond any possible interaction or observation from our perspective. So here we sit, in this quiet moment, at the center of our own observable universe, a tiny island of awareness. Beyond our observable universe, there is more universe, vast and unexplorable by us. And beyond that, inflation continues, carrying away the other level 1 universes, which we will never know, forever beyond our reach. Many questions, of course, still gently linger, none less profound than just how a universe truly emerges, crystallizes from the eternal inflation. Some scientists have suggested the process is akin to the formation of bubbles when you gently open a soda bottle, where gas comes out of solution and forms discrete bubbles. And it is this bubble nucleation, this gentle act of formation, that the theory suggests cements the fundamental properties of the universe it forms. Not just the overall properties, like its general size, but the intricate details that govern its very being. This includes, astonishingly, the very laws of physics themselves. This means that in some of these bubble universes, the fundamental forces of nature, gravity, electromagnetism, The nuclear forces will be profoundly different from our own. In others, the masses of the fundamental particles electrons, quarks, neutrinos will be different, perhaps making atomic stability impossible, or making stars burn too quickly. And in others again, there might be more or fewer dimensions of space and time than the four we so readily experience. Physicists have pondered deeply what these other universes, with their varying laws and dimensions, would be like, and they have arrived at a stark, yet quiet conclusion. Virtually all of these other universes would be dead and sterile, utterly lacking the specific complexity and precise conditions essential for the emergence and sustenance of life. They would be cold, chaotic, or too simple to ever host the vibrant dance of chemistry that leads to biological complexity, though within this endless, vast sea of dead universes, with their unfavorable laws, there would be tiny pockets of habitability, incredibly rare islands where the conditions, the laws, the constants, just happen to align perfectly for the possibility of life. And it is no surprise, of course, that this is precisely where we find our universe, in this Level 2 multiverse. Our own Level 1 multiverse, our observable universe and all its infinite copies, is just one of the incredibly lucky few that can host the complexity of life. And thus, consciousness capable of pondering its own existence, the apparent fine-tuning of our physical laws, which once seemed so miraculous, is then little more than a statistical fluke, a single, incredibly fortunate roll of an infinite dice across a higher infinity of possibilities. It's a thought that, while perhaps unsettling to some, brings a profound sense of gentle wonder at our improbable existence. Welcome back, gentle traveler, to our quiet exploration of the cosmos. Take another soft breath now, feeling the subtle flow of air, the steady beat of your heart, as we ponder the vastness of the Level 2 multiverse, where even the laws of physics might vary from one bubble universe to another. Let us remember that these are not rigid dogmas, but gentle ideas, whispered possibilities that stretch the very edges of our understanding. There is no right or wrong answer here, only the profound peace that comes from embracing the boundless mystery. This concept of Level 2 multiverses, born from the beautiful and messy implications of eternal inflation, is not the only way such a higher-order reality has been proposed. Indeed, there are other theories that suggest our Level 1 existence. Our observable universe with its infinite copies would only be a tiny fragment of something far grander. And in fact, one of the key architects of that very new theory of inflation we just discussed, Paul Steinhardt, has since played a pivotal role in a whole new, utterly captivating idea. To truly appreciate this next perspective, let us first cast our minds back to ancient wisdom, to the profound and cyclical cosmology of Hindu philosophy. In this rich tradition, the universe is not seen as having a definite beginning or an absolute end. Instead, the universe is cyclical, a grand cosmic breath, with each cycle lasting for an immense period of 320,000 years, each cycle. In this beautiful vision, starts with a moment of rebirth and perfection, a golden age of enlightenment and ideal existence. As it ages, the universe gradually degenerates and decays, slowly losing its initial purity and harmony, before eventually reaching a point of ultimate destruction. But this destruction is not a finality, it is merely a prelude to a magnificent rebirth, leading into the next grand cycle, and it's a timeless dance of creation, preservation, and dissolution, a perpetual cosmic motion. But what of the physical universe? The one described by our equations and observations, could it truly be cyclical in this way? Since the dawn of modern cosmology in the early 20th century, many brilliant minds have pondered this very question. In the 1920s, physicists, including none other than Albert Einstein himself, explored this intriguing possibility within the elegant framework of the cosmological equations derived from his theory of general relativity. The prospect for a cycling universe, one that continually expands and contracts, did indeed exist. The idea that our universe was just one phase of an infinitely repeating cycle was, for many, a far more comforting thought than a universe born from absolute nothingness. A concept that seemed to defy intuition. It offered a kind of cosmic immortality, a reassurance of continuity. However, a persistent and nagging problem always lingered. A quiet, unavoidable shadow that haunted the cyclical universe idea. The problem of entropy. Entropy, in its simplest form, is a measure of disorder, a relentless, inexorable tendency for the universe to run down, to spread out, to become less structured and more uniform. At every moment, through every process, whether it's a star burning or a rock weathering, useful energy is being subtly degraded into useless energy, becoming less available to do work. Life on Earth, in all its vibrant complexity, is completely governed by such processing of energy, constantly fighting against the tide of increasing disorder, but never truly winning in the long run. Think of a fire. It takes ordered wood and transforms it into chaotic ash and diffuse heat. Or imagine a cheetah, swiftly chasing its prey, converting the ordered chemical energy of food into the chaotic kinetic energy of movement and dissipated heat. Energy, in its total flow, balances perfectly energy and equals energy out, but the entropy, the irreversible movement from potential order to greater disorder, always continues to increase across the universe. This is an unavoidable conclusion. At the end of time, the total disorder will be profoundly greater than at the start. There is no known way, within the standard laws of physics, to escape this quiet yet relentless increase. But if a universe is just part of an endless, perhaps infinite, cycle, how can this be reconciled with the constant increase of entropy? Every cosmos, in this scenario, would begin encumbered with the disorder from all the universes that existed before it. If each cycle adds more disorder, and there is an endless chain of cycles, then logically, our current universe should be incredibly disordered, far more so than it appears. The inexorable increase of entropy, this quiet, relentless march towards maximum disorder, seem to doom the beautiful idea of a perfectly cyclical universe, relegating it to the forgotten ideas of science, a dream that couldn't quite fit into the cold logic of thermodynamics. Yet, sometimes, it is incredibly hard to completely kill a profound scientific idea, especially one that offers such a comforting sense of cosmic rhythm. And so, the concept of a cyclical universe has itself been, quite fittingly, recycled. Recent Nobel Prize winner, the brilliant physicist Roger Penrose, proposed a fascinating and highly speculative theory called conformal cyclic cosmology. His idea is subtly different, elegantly attempting to bypass the entropy problem. Penrose suggested that in the extreme, almost unimaginable distant future of our universe, when the Big Freeze has truly taken hold, all matter must eventually decay away into nothingness, leaving behind only radiation and possibly a few black holes that will eventually evaporate. And critically, in his model, the resulting empty, cold, and immensely expanded universe will continue expanding into eternity. When it is large enough and empty enough, it will become a very simple, featureless place of vast, uniform void. And here is the profound twist. This state of ultimate emptiness and uniformity is mathematically equivalent to the state of our own universe at the very start of the Big Bang. Infinitely dense but effectively featureless. Penrose then hypothesized that the past and the future, in this extreme scenario, are effectively one, constantly cycling between cosmic birth and cosmic death. It's a captivating vision, where the far distant future smoothly transitions into a new beginning, a never-ending cosmic loop. But Penrose's conformal cyclic cosmology is just one example of how the cyclical idea has been reborn. In the 1980s, Another insightful physicist, Lee Smolin, offered a truly radical and original proposal. He suggested that a baby cosmos could be created when black holes form, as a black hole violently tears space and time at its singularity. This very tear, this profound disruption, could give birth to an entirely new universe. This wouldn't be a birth within the existing cosmos, but a process that spawns a completely new universe of space and time, separate and distinct from its parent. If this idea holds even the faintest spark of truth, then every single second, a new cosmos is quietly, miraculously born from a stellar death in our own universe. Our universe, then, would be a cosmic nursery, constantly giving rise to new realities. Smolin, however, went even further. Drawing a bold analogy from Darwinian evolution, he wondered if these baby universes, born from black holes, could mutate and be slightly different to their parent universe. These differences, he speculated, would lie in the fundamental laws of physics underlying each cosmos. If the mutation is too severe, perhaps gravity is too weak, or there aren't enough atoms to form stars, such a baby universe would be an evolutionary dead end, unable to reproduce further black holes. But those universes that can form stars, and thus can form black holes, would beget more baby universes over immense cosmic timescales. These star-forming, black hole-producing universes would eventually come to dominate in the evolutionary tree of this particular multiverse, as stars are absolutely essential for the habitability of our own universe. Smolin's multiverse. Driven by this process of cosmic natural selection, could be teeming with life, a cosmic jungle of thriving realities. Of course, there is a lot of uncertainty and what physicists sometimes gently call hand-waving in Smolin's theory. While it is certainly intriguing to ponder, not everyone is convinced by its full implications. And finally, the cyclical universe was recently reborn once again, but this time, dramatically, in fire. Think of the phoenix, the immortal bird of Greek mythology. It lives its life in immense cycles, dying in old age in a spectacular burst of flames. But from its own ashes, the phoenix is reborn, pristine and vibrant, to live its life again, a symbol of endless renewal. And this is precisely where Paul Steinhardt, whom we encountered earlier, reappears in our story in conjunction with Neil Turok. He has since come to gently reject his earlier inflationary theory, or at least to propose an alternative that he finds more compelling, and has put forth a new Level 2 multiverse concept, the ekpyrotic universe, developing out of the highly complex framework of string theory. The ekpyrotic model posits that our entire universe floats in higher dimensions, much like a thin sheet or brain gently blowing in an unseen wind. Here, cosmic rebirth occurs not from an explosion of a point, but when multiple cosmic sheets, immense, multi-dimensional membranes, collide in a spectacular, fiery embrace. Huge amounts of energy are released during this collision, generating all the matter and radiation in our cosmos. Crucially, the newborn universe that emerges from this fiery collision begins with incredibly low entropy, the very problem that plagued earlier cyclical universe models, where each cycle started with more disorder. In the ekpyrotic vision, the Phoenix universe truly rises from the ashes, cleansed and renewed, ready to begin its grand cycle again. Solving the entropy problem with elegant, fiery collisions. Today, the ekpyrotic universe has relatively few true supporters compared to eternal inflation. Many physicists still grapple with the mind-bending notion of these cosmic sheet universes, gently floating and colliding in higher dimensions. It requires a profound shift in perspective, moving far beyond our familiar 3 dimensions of space. However, despite its niche status, this concept has recently gained widespread attention, thanks to its unique approach to cosmic origins and its elegant solution to the entropy problem in cyclical models. And the answer to why it's gaining attention may lie in one of the most complex, yet potentially most all-encompassing, and mind-blowing theories of all, a theory that attempts to unify everything we know about the universe into a single beautiful framework. Welcome, gentle voyager. As we continue our quiet descent into the heart of cosmic mysteries, take a soft, calming breath. Feel the subtle energy that vibrates within you, connecting you to all things. We are now about to embark on a journey into one of the most ambitious and mind-bending quests in all of science, the search for a theory of everything. A single, elegant framework that can describe the entire universe. It is a dream, a goal, that has captivated some of the brightest minds for centuries, a quiet whisper urging them to unify the disparate threads of reality. Our story, for this segment, begins not with a brilliant flash of scientific insight, but with a rather unconventional path. Imagine Ed Witten, a name that echoes with profound mathematical genius in the world of physics, but whose early life took a meandering route. In 1971, he completed an arts degree, delving into the rich tapestry of history and linguistics. He then tried his hand at journalism, seeking to understand and communicate the stories of the world. He even ventured into the often turbulent waters of politics, perhaps hoping to shape the narratives of human society. Eventually, he enrolled in a graduate program in economics, trying to decipher the complex flows of wealth and resources. But in a quiet moment of introspection, he realized these paths were not his true calling, and he gently dropped out. By 1976, after much searching, he had finally found his true niche. His intellectual home, he completed a PhD in fundamental physics, setting his sights on the deepest questions of how the universe truly works. What set Witten apart? What made his mind a unique instrument in the symphony of physics? Were his extraordinary mathematical insights, particularly concerning the topology of space and time. He could see shapes and connections in the abstract realms of mathematics that others could only dimly perceive. His brilliance was so profound that in 1990 he was awarded the Fields Medal for his groundbreaking work. This prestigious award is often referred to as the Nobel Prize of Mathematics, and it is almost exclusively given to mathematicians. That a physicist like Witten received it underscores the exceptional, almost artistic, nature of his contributions to our understanding of the universe's mathematical underpinnings. But by this time, Witten had already set his sights on bigger things, on one of the biggest dreams in physics, a single theory that encompassed everything we know about the universe. This was the elusive theory of everything, the ultimate prize, the holy grail of physics. It's a dream that suggests there is an underlying unity to all of nature's forces and particles, a single, elegant equation or set of principles from which all the complexity of reality could be derived. Just why has this search been so incredibly hard, so elusive, leading so many brilliant minds down paths that ultimately led to quiet cul-de-sacs? The fundamental challenge lies in a deep, perplexing schism in our current understanding of the universe. Of the four fundamental forces of nature, the strong nuclear force, the weak nuclear force, electromagnetism, and gravity, three are beautifully and consistently described by the language of quantum mechanics. This is the physics of the incredibly small, the realm where particles can be in multiple places at once, and where uncertainty is a fundamental part of reality. These three forces, which govern everything from the binding of atomic nuclei to the flow of electricity, dance to the tune of quantum rules. Our best description of gravity, however, is a different symphony altogether. It is Einstein's monumental general theory of relativity, a distinctly non-quantum theory. In general relativity, gravity is not a force in the traditional sense, but a manifestation of the curving and bending of space and time itself. Caused by the presence of mass and energy, it describes the large-scale structure of the cosmos with breathtaking accuracy. From the orbits of planets to the expansion of the entire universe, the profound disconnect, the deep, philosophical itch that has long bothered physicists. Is this why are the forces of nature seemingly written in two different mathematical languages? There is a powerful feeling, a deep-seated desire, almost a spiritual longing among physicists, that the true mathematics of the universe should be one neat, single, all-encompassing theory that elegantly describes all the physics of the universe, from the smallest quantum foam to the largest cosmic structures, and physicists have searched for this unifying theory for a very, very long time. Early, valiant attempts to unite gravity and electromagnetism were made by brilliant thinkers like Theodore Kaluza and Oscar Klein. Their intriguing idea involved adding more dimensions to Einstein's relativity, imagining a hidden, curled-up dimension that could somehow unify these forces. But ultimately, despite their ingenuity, they failed in their grand quest. The path to a theory of everything is littered with the quiet dreams of failed theories. Grand monuments to brilliant minds who pursued this elusive goal but did not quite reach it. This includes Einstein himself, who spent the latter part of his life in a solitary, determined, but ultimately unfulfilled pursuit of a unified field theory. Other great names like Hermann Weyl, Arthur Eddington, and David Hilbert also left their mark on this winding, difficult path. By the 1970s, a brave new contender, whispered into existence by the collective efforts of many physicists, had been proposed supergravity. This theory was based upon an incredibly elegant mathematical formalism known as supersymmetry. Supersymmetry suggested a beautiful symmetry in nature for every known fundamental particle. There should be a corresponding superpartner particle with slightly different properties. For electrons, there should be selectrons. For quarks, squarks. And most counterintuitively, perhaps even magically, the mathematics of supergravity seemed to work best in a universe with 11 dimensions. This was a radical departure from our familiar 4 dimensions of space-time, suggesting that reality might be far richer and more complex than we perceive. Physicists were incredibly excited. It felt like they were finally on the verge of cracking the code, of weaving together gravity with the other forces. But as scientists peered more deeply into these complex, elegant equations, things slowly, gently, began to unravel. The universe predicted by the ideas of supergravity simply didn't match the one we inhabit. Its properties, its particles, its very structure seemed subtly different from the reality we observe. And so, eventually, supergravity quietly, gracefully fell by the scientific wayside. Another beautiful idea that, for all its promise, couldn't quite capture the full truth of the cosmos. But, as we have already seen, it can be incredibly difficult for truly profound scientific theories to completely die and disappear, especially those with the powerful prefix super. And so, from the intellectual fertile ground that supergravity had prepared, a new, even more ambitious contender was born. In 1984, superstring theory quietly emerged in the brilliant minds of Michael Green and John Schwartz, igniting a new wave of excitement and hope. The key poetic idea of superstrings is remarkably simple, yet profoundly revolutionary. All fundamental particles, the electrons that orbit atoms, the quarks that make up protons and neutrons, the elusive neutrinos are not point-like dots at all. Instead, they are all really the same thing, tiny, incredibly thin, vibrating loops of stringy stuff. Imagine the universe as a grand, cosmic instrument, and these fundamental particles are just different musical notes played on these vibrating strings. One particular note or vibrational pattern corresponds to an electron, another distinct note to a quark, and so on. This elegant idea promises to unify matter and forces in a single, beautiful framework, and just like its super ancestor, supergravity, Superstring theory needs far more dimensions than we experience in our day-to-day lives. In its earliest mathematical form, superstring theory was initially written in a mind-boggling 26 dimensions. However, as the theory matured and evolved, things eventually settled down to a more manageable 11 dimensions, echoing the structure that supergravity had also suggested. This convergence was seen as a powerful hint that they were on the right track, that these extra dimensions were not just arbitrary mathematical constructs, but perhaps a fundamental aspect of reality. But if there are 11 dimensions, why do we only experience 4, 3 of space and 1 of time? A clever mathematical way was found to hide these extra dimensions, a process known as compactification. Unlike our everyday vast dimensions of up, down, and across, these supposed extra dimensions were thought to be curled up on a microscopic scale, incredibly tiny, so small that we cannot perceive them. And these curled-up dimensions could take on incredibly complex, bizarre geometrical shapes, often referred to as Calabi-Yau manifolds. Imagine them as intricate, multi-dimensional knots existing at every point in our familiar four-dimensional space. And just as we cannot directly experience the individual atoms in the air, or the subatomic particles within them, we cannot experience the existence of these microscopic, curled-up dimensions. Again, physicists were filled with palpable excitement. Again, they truly thought that they were about to arrive at the theory of everything, a complete, elegant description of the universe from first principles. And again, with a gentle, almost sad sigh. Their hopes were dashed. The problem wasn't that string theory was wrong, but that it was too right, or rather, too flexible. They had hoped that a single unique mathematical framework for the theory of everything would emerge, providing definitive answers. But the mathematical complexity grew exponentially, and instead of converging, ideas began to splinter. In total, there were 5 different versions of string theory, each seemingly following its own distinct path towards enlightenment, each with its own set of rules and predictions. This multiplicity of theories, rather than a single unifying one, was deeply frustrating. By the mid-1990s, frustrations among string theorists had reached a quiet boiling point. The dream of a unique theory of everything seemed more distant than ever, and that was when, in 1995, at the annual String Theory Conference held at the University of Southern California, Ed Witten, the brilliant mind we met earlier, stepped forward and put a new, radical idea on the table. Perhaps, he gently suggested, these 5 differing theories weren't so distinct after all. Perhaps they were all simply different facets of the same underlying theory, intrinsically linked, like different projections of a single, higher dimensional object. It was from this profound revelation, this quiet moment of insight, that M theory was born, and the second superstring revolution began. No one, it seems, can quite remember what the M in MA theory officially stands for. Some whisper mystery, reflecting its profound enigmatic nature. Others suggest magic, acknowledging its almost supernatural elegance in unifying complex ideas. But to many, particularly those working with its concepts, it stands for membrane, or brain, reflecting how the one-dimensional strings of string theory are not just lines, but can be drawn out into higher dimensional sheets or membranes within the universe's higher dimensions. This concept of brains existing within a higher dimensional space, where our entire universe might just be one such brain, eases some of the immense mathematical issues that faced earlier string theories, allowing for a more consistent framework. However, it is crucial to understand that it does not solve them entirely, and in truth, M theory isn't yet a completed theory in the traditional sense. It is more of an idea, a grand dream, a guiding goal towards which physicists are still tirelessly working. It is a framework, a blueprint, for the ultimate theory of everything. However, it has brought one profound, quiet truth into sharp relief, reshaping the very nature of the quest. The original hope, the initial aspiration for the theory of everything, was that it would be pure and unique. It would definitively explain why the electron has the exact mass it does, and why gravity possesses its precise strength, implying that these values were uniquely determined by fundamental principles. That comforting hope. The idea of a single, unique explanation for everything largely died with the emergence of M-theory. M-theory, in its current conceptual form, predicts that due to the intense heat and energy in the very first moment after the Big Bang. The early universe would have been incredibly featureless and simple, as the universe then gradually cools. The fundamental features of physics, the specific laws and constants, would begin to crystallize out, much like a liquid solidifying into a specific crystal structure. But here's the crucial, and perhaps mind-bending, implication of M-theory. This crystallization of the laws of physics is not unique. There are, it suggests, uncountable, perhaps even infinite, ways that this crystallization can occur. Each different crystallization would result in different fundamental physics, different particle masses, different strengths for the forces, even different numbers of dimensions that become large and observable. Physicists refer to this myriad, this vast, incomprehensible number of possible combinations of the laws of physics. As the string theory landscape, it's a conceptual landscape of possibilities, a rolling, multi-dimensional terrain where every peak and valley represents a unique universe with its own distinct physics. How many solutions, how many potential universes with different laws are out there in this landscape? The answer, whispered by the mathematics, is a number so vast it dwarfs even the largest numbers we have discussed before. It is beyond comprehension, implying an almost endless variety of cosmic realities, a silent testament to the universe's infinite creativity. Welcome, gentle consciousness, as we continue our quiet descent into the boundless possibilities of the cosmos. Take a slow, peaceful breath now, feeling the subtle connection between your inner world and the immense expanse beyond. We have journeyed through the idea of a universe crafted by precise, finely tuned laws, and then seen how theories like eternal inflation and M-theory suggest a vast landscape of possibilities. Where these very laws might vary, this isn't just a scientific concept. It's an invitation to contemplate the profound richness and diversity of existence itself. So, how many solutions, how many potential universes with different laws are truly out there in this vast string theory landscape? The number is so astronomically immense that it defies simple human comprehension. It's often estimated to be around 10^500 different possibilities. To put that into a gentle perspective, imagine the number of atoms in the entire observable universe. That's roughly 1080. The number of possible universes in this landscape is not just larger, it's a number that utterly dwarfs the number of atoms in our known reality. Each of these 10^500 possibilities represents a distinct set of physical laws, a unique configuration of fundamental forces, particle masses, and even the dimensions that unfurl into existence. This staggering number leads us to a profound and quiet realization. If M-theory is indeed a step towards the ultimate theory of everything, and if its predictions about this vast landscape are correct, then the question of why our universe has its particular laws of physics takes on a new, gentle answer. It's not necessarily that our laws are uniquely chosen by some grand cosmic principle. Instead, our universe simply occupies one incredibly tiny, specific point in this unimaginably vast landscape. It's a bit like a single grain of sand on an infinite beach, where every other grain is a different universe with different rules. This leads us directly to the next level in Max Tegmark's classification of multiverses level 3. If level 1 dealt with infinite copies of our universe in an infinitely large space, and Level 2 with universes possessing different laws of physics. Level 3 delves into a realm that might feel even more intimate, even more mind-bending. It asks, what if there are universes that are not merely far away in space, or separated by different physical laws, but are actually woven into the very fabric of reality at a deeper, more fundamental level? To grasp this, we need to gently explore one of the most counterintuitive and profound concepts in modern physics: quantum mechanics. You've probably heard its name whispered in hushed tones, a theory that governs the strange, often illogical behavior of the very smallest particles that make up everything around us. It's the language of the subatomic world, a realm where our everyday intuition about cause and effect, position and momentum, often breaks down. One of the most unsettling, yet strangely beautiful, aspects of quantum mechanics is that at the smallest scales, particles don't behave like solid, predictable objects. Instead, they exist in a hazy state of possibilities. Before you measure it, a quantum particle, like an electron, doesn't have a single, definite position or momentum. It exists in a superposition of all its possible states simultaneously. Imagine a single coin spinning in the air before it lands. It's neither heads nor tails, but somehow both at the same time. Only when you observe it, when it lands, does it choose one state. This leads to the famous Schrödinger's cat thought experiment, a gentle yet unsettling paradox. Imagine a cat in a sealed box with a vial of poison connected to a quantum event. If the quantum event happens, the poison is released and the cat dies. If it doesn't, the cat lives, according to quantum mechanics, until the box is opened and the cat is observed. The cat is neither alive nor dead, but in a superposition of both states. Only observation forces it to choose a definite reality. This idea of superposition, of things existing in multiple states until observed, presents a profound challenge to our understanding of reality. When we are the observers, what happens? Does our act of observation, our conscious awareness, somehow collapse the wave function, forcing the quantum possibilities into a single, definite reality? If so, what is the nature of that collapse and where do the other possibilities go? This is where the many worlds interpretation of quantum mechanics gently steps onto the stage. Proposed by Hugh Everett III in 1957, this interpretation offers a radical, yet remarkably elegant answer to the quantum measurement problem. Instead of the wave function collapsing and the other possibilities disappearing, Everett suggested something truly mind-bending: all possible outcomes of a quantum measurement actually occur, each in its own separate, distinct universe. Imagine that spinning coin. When it lands, in our universe, it might be heads, but in another, parallel universe, which branched off at that very quantum moment, it landed tails, and in yet another, it somehow remained suspended in the air. For every quantum decision, for every particle interaction, the universe branches into all possible realities. This means that at every moment, with every subatomic interaction, with every thought, with every tiny fluctuation, the universe is constantly splitting, creating new, parallel realities. If this interpretation is true, then your own consciousness is constantly branching. Every decision you make, every choice you don't, every path not taken, all these possibilities are actualized in different branches of this vast quantum multiverse. There is a version of you who woke up 5 minutes earlier, a version who chose a different shirt, a version who is not reading these words at all, and a version of you who is. This level 3 multiverse is not out there in distant space. It's right here, woven into the very fabric of reality. A continuous, branching tree of possibilities unfolding in every instant. The implications are profound. If the many worlds interpretation is correct, then there are infinitely many versions of you, living out infinitely many variations of your life. each in its own unique quantum branch. This means that every possible quantum outcome, no matter how improbable, is realized somewhere. It's a universe, or rather, a multiverse, of limitless possibilities, constantly burgeoning into new realities. This level 3 multiverse is unique because these parallel universes are not separated by vast distances in space, nor by different physical laws. Instead, they are distinct quantum branches of reality, existing in the same physical space and time, but separated by their differing quantum outcomes. They are nearby in a very strange quantum sense. Perpetually created by the universe's own probabilistic nature, this can feel a bit overwhelming, a touch unsettling, to think of so many versions of oneself existing. But perhaps there is a quiet peace in it too. It suggests that every possibility, every choice, every potential path is honored, is actualized. Somewhere in this grand quantum tapestry, you are living one beautiful, specific thread in an infinite weave. It reminds us that reality, at its deepest level, is far more subtle and abundant than our everyday senses can perceive. This gentle descent into the quantum realm, into the splitting realities of the level 3 multiverse, reminds us that the clouds of mystery aren't just geographic or cosmological. They linger around us, within us, in every fleeting quantum moment. The universe is not just vast in space and time, but infinitely deep in its possibilities. Now, let us gently ascend to the very pinnacle of Max Tegmark's multiverse ladder, to level 4. This level is, perhaps, the most abstract, the most mind-bending, and yet, in its own way, the most elegant. It is the idea that every conceivable mathematical structure, every self-consistent set of mathematical equations, corresponds to its own distinct physical reality, its own universe. Think about the fundamental nature of mathematics. It is often described as the language of the universe, the underlying blueprint from which physical laws emerge. From the simplest arithmetic to the most complex equations of quantum field theory or general relativity, mathematics provides the framework for describing reality. But what if mathematics isn't just a description of the universe, but is the universe? This is the core idea of the level 4 multiverse. It suggests that any mathematically consistent structure, any abstract system of relationships and rules that can be imagined, actually exists as a real, physical universe. If you can write down a set of equations that describe a self-consistent reality, then that reality exists somewhere, in some form. This means that universes with entirely different fundamental mathematical structures, not just different values for constants, but different geometries, different logics, different dimensions, even different numbers of fundamental particles all exist. This takes the concept of different laws of physics to its ultimate extreme. In a level 4 multiverse, our universe, with its specific set of mathematical laws, quantum mechanics. General relativity, the standard model of particle physics, is just one instance out of an infinite collection of possible mathematical structures. There could be universes where the speed of light is infinite, or where time flows in multiple directions, or where gravity is a repulsive force, or where particles interact in ways utterly alien to our understanding, as long as the mathematical description is consistent. The universe exists. This idea is incredibly abstract. Bordering on philosophical, it suggests that mathematics is not something invented by humans, but rather something discovered an inherent structure of reality that exists independently of us. And if all mathematically consistent structures exist, then the universe of possibilities is truly, utterly infinite in a way that dwarfs even the infinite spatial expanse of level 1 or the infinite quantum branches of level 3 in a level 4 multiverse. The fine-tuning of our universe for life isn't a fluke, it's a certainty. Somewhere in the infinite collection of mathematical structures, there must be a structure that allows for complexity, for stars, for planets, and for consciousness. Our universe just happens to be the structure, It removes the need for any special explanation for our existence, positing instead that all possible self-consistent explanations exist. This can be a deeply peaceful thought. It suggests that reality is far richer and more diverse than we can ever imagine. A boundless tapestry woven from pure mathematical truth. It invites us to surrender to the idea of infinite creativity, where every conceivable form of existence is given its space. And so, we complete our ascent of Max Tegmark's multiverse ladder, from the infinite copies in Level 1 to the varying physics of Level 2, the branching quantum realities of Level 3, and finally to the ultimate mathematical existence of Level 4. Each step has revealed a deeper, more profound sense of the universe's incredible scale and its boundless possibilities. But is this the end of the story? Have we finally dispersed all the cosmic clouds? Not quite, even as these grand multiverse theories proliferate. New questions, new layers of mystery, continue to emerge. For example, some physicists find the concept of an infinite number of selves in Level 3 unsettling, and the abstract nature of Level 4 almost untestable. The debate continues. The gentle scientific exploration persists. The universe, in its wisdom, always holds more secrets, always invites further wonder. So, as you gently drift into this moment of quiet, ponder the magnificent implications of these multiverses, whether they are infinite copies of you, or universes with different laws, or branching quantum realities, or even universes of pure mathematical truth. They all point to a cosmos far grander, far more diverse, and far more mysterious than we once imagined. There is a profound tranquility in accepting this boundless possibility, in letting go of the need for a single, simple answer, and instead, embracing the quiet, endless wonder of it all. Welcome back, gentle wanderer, to our serene journey through the boundless tapestry of the cosmos. Take a soft, deep breath, allowing your thoughts to settle like dust motes in a shaft of sunlight. We have ventured far, from the gentle mapping of our early Earth to the dizzying heights of the multiverse, where infinite copies of you might exist, and where the very laws of physics dance to a different tune in countless other realities. Now, as we continue our quiet exploration, let us turn our attention to one of the most fundamental and intimate connections we share with the universe, light itself, and how it paints our cosmic understanding. Imagine light not just as something that illuminates your world, but as an ancient messenger, carrying tales from the deepest reaches of time and space. Every ray of sunlight that gently warms your skin, every shimmer from a distant star you might glimpse on a clear night, is a tiny fragment of the universe's grand narrative. Light is our primary window to the cosmos, and understanding its nature has been a profound quest, quietly revealing secrets about the immense distances and the very history of everything. For much of human history, light was a mystery. People knew it came from the sun, from fire, from stars. But its true nature, its speed, its journey across the vast emptiness of space, remained largely unknown. It was simply there, illuminating the world. But then quiet curiosity began to stir, and scientists began to gently probe its secrets. One of the most astonishing realizations about light is its incredible, yet finite, speed. Imagine a cosmic race. Nothing in the universe can travel faster than light. It races across the vacuum of space at approximately 299,792,458 meters per second, a speed so immense that it wraps around the Earth over 7 times in a single second. This isn't just an impressive number, it's a fundamental constant of the universe, a fixed speed limit for information itself. This gentle, unwavering speed is crucial to how we perceive the cosmos, because light travels at a finite speed. Every time you look at something distant, you are not seeing it as it is now, but as it was when the light left it. When sunlight touches your face, you are feeling light that left the sun about 8 minutes ago. So, you are seeing the sun not as it is in this very instant, but as it was 8 minutes in the past. This makes every glance into the night sky a journey through time. Consider the stars you see twinkling above, the light from our nearest star, Proxima Centauri. Takes a little over 4 years to reach us. This means when you look at Proxima Centauri, you are seeing it as it was 4 years ago. The beautiful Pleiades star cluster, sometimes called the Seven Sisters, twinkles with light that left those stars about 440 years ago. So, you are seeing them as they appeared around the time Galileo first turned his telescope to the heavens. Now, stretch your mind further. To the galaxies we discussed, the light from the magnificent Andromeda Galaxy, our closest large galactic neighbor, has traveled for about 2.5 million years to reach your eyes. This means when you gaze at Andromeda, you are seeing it as it appeared 2.5 million years ago, long before humans walked the Earth, for those incredibly distant galaxies, the ones billions of light years away. Their light left them billions of years ago. When the universe was much younger, we are seeing them as they were in their cosmic infancy, revealing what the early universe looked like. This concept turns our telescopes into time machines. The farther we look into space, the further back in time we are seeing. It's as if the universe is a vast photograph album, and the pages closest to us show the present, while the pages further away show increasingly ancient times. When we observe the cosmic microwave background radiation, that faint, uniform glow filling the sky, we are seeing light that has traveled for over 13.7 billion years. This is the oldest light in the universe that we can detect. A direct glimpse into the universe when it was a mere baby, only about 380,000 years old. It is the very afterglow of the Big Bang, a cosmic echo that whispers tales of creation. The journey of light through the cosmos is not always a straight, unhindered path. The universe is a dynamic, evolving place, and light often interacts with its contents. Sometimes, light is absorbed by dust clouds or gas, only to be re-emitted at a different wavelength, like a warm blanket absorbing sunlight and then radiating heat. Sometimes, it is scattered, like sunlight hitting water droplets to create a rainbow, or blue light being scattered by Earth's atmosphere to make the sky blue. But one of the most fascinating ways light interacts with the cosmos is through gravitational lensing. Imagine space and time not as a fixed, flat stage, but as a flexible fabric. Massive objects, like galaxies and clusters of galaxies, bend and warp this fabric, creating dips or wells in spacetime. When light from a distant object passes near one of these massive structures, its path is bent, just as light bends when it passes through a glass lens. This phenomenon is called gravitational lensing. Gravitational lensing allows us to see objects that might otherwise be too faint or too far away to detect directly. It can magnify distant galaxies, making them appear brighter and larger, much like a magnifying glass helps us see tiny details. Sometimes, it can even create multiple images of the same distant galaxy, as the light from that galaxy takes different warped paths around the massive foreground object before reaching us. These distorted, often arc-shaped images are beautiful cosmic mirages, silent testimony to the incredible warping power of gravity, beyond helping us see distant objects. Gravitational lensing also serves as a powerful tool to map the distribution of matter in the universe, especially the elusive dark matter. Since dark matter does not interact with light in any way that we can directly observe, we cannot see it through conventional telescopes. However, dark matter does have mass, and therefore it exerts a gravitational pull, bending spacetime, by observing how light from distant galaxies is lensed and distorted. Astronomers can deduce the presence and distribution of invisible dark matter, slowly unveiling the hidden scaffolding of the cosmos. It's like seeing the invisible wind by observing how it bends the branches of trees. This understanding of light, of its journey through time and space, of its interactions with matter and the very fabric of spacetime, has profoundly shaped our modern cosmology. It is how we know the universe is expanding, how we estimate its age, and how we map its grand structures. Every photon, every tiny packet of light, carries a wealth of information, a silent whisper from the past, an echo of cosmic events. And what about the future of light in the cosmos? As the universe continues its accelerating expansion, driven by dark energy, distant galaxies are moving away from us at ever-increasing speeds. The light from these galaxies, as it travels across vast and expanding space, gets stretched, its wavelength elongated, shifting towards the red end of the spectrum. This phenomenon is called cosmological redshift for very distant galaxies. This redshift is so profound that their light is stretched out of the visible spectrum entirely, shifting into the infrared or even radio wavelengths, becoming invisible to our eyes. Eventually, as we discussed, in perhaps 100 billion years, all galaxies beyond our local group will have receded so far, and their light will be so redshifted that they will simply vanish from our observable sky. The night sky of the distant future will be a vast, empty blackness, devoid of the twinkling lights of distant galaxies, with only the stars of our own local galactic cluster remaining. The cosmic messengers will cease to reach us, and our window to the distant universe will close. This is a quiet, almost melancholic thought, a reminder of the fleeting nature of even cosmic visibility. Yet, even in that ultimate darkness, the principles of light will still hold. The universe will continue to exist, just unseen, and the understanding we have gleaned from light's journey will remain, a testament to humanity's tireless quest to understand its place in the grand scheme of things. So, as you rest in this moment, allow the concept of light, this ancient traveler, to fill your mind. Imagine its long, unwavering journey from distant stars and galaxies, carrying stories of cosmic births and deaths, of immense distances and unimaginable times. Feel its gentle touch upon your being, a constant connection to the very origins of existence. There is a profound peace in knowing that you are bathed in light that has traveled for eons, linking your present moment to the deep, silent past of the universe. Welcome, gentle consciousness, to the continuing soft flow of our cosmic narrative. Take another peaceful breath, allowing the concept of light's vast journey to settle gently within your mind. We've seen how photons, tiny messengers from the past, paint our view of the distant cosmos. Now, let us turn our gaze not outwards but inwards, to one of the most profound and mysterious aspects of our own existence, the nature of time itself. Time, for us, feels so immediate, so linear. It's the relentless ticking of a clock, the progression from morning to night, from birth to old age. We experience it as a continuous, unyielding flow, always moving forward, never backward. But what is time? Really, is it a fundamental river, flowing independently of everything else? Or is it something that emerges from the universe's fabric, intimately connected to space and matter for centuries, even millennia? Philosophers and scientists have grappled with this elusive concept. Ancient thinkers often viewed time as cyclical, like the seasons or the phases of the moon, a repetition of patterns. But with the rise of modern science, particularly the work of Isaac Newton, time came to be seen as an absolute, universal constant, an invisible, unchangeable background against which all events unfolded. Newton imagined time as a straight, infinite line, flowing uniformly for everyone, everywhere. However, this comforting, intuitive picture of time was profoundly challenged and ultimately reshaped by Albert Einstein's revolutionary theories of relativity, with his special theory of relativity. Published in 1905, Einstein unveiled a startling truth: time is not absolute. Instead, it is relative, meaning its passage can vary depending on the observer's motion. This phenomenon is known as time dilation, Imagine two gentle travelers. One is sitting quietly, perfectly still. The other is traveling at an incredibly high speed, close to the speed of light, according to Einstein. Time would pass more slowly for the fast-moving traveler compared to the one at rest. This isn't just a theoretical curiosity, it has been rigorously confirmed by countless experiments. Even in our everyday lives, GPS satellites, which orbit Earth at high speeds, have atomic clocks that run slightly slower than identical clocks on the ground. Without accounting for this time dilation, your GPS navigation would quickly become inaccurate. This means that time is not a separate, rigid background, but is interwoven with space to form a four-dimensional fabric called space-time. Events that are simultaneous for one observer might not be simultaneous for another, especially if they are moving relative to each other. It's as if each observer has their own personal flow of time, though the differences are only noticeable at very high speeds or in very strong gravitational fields. Then came Einstein's general theory of relativity in 1915, which deepened this understanding even further. General relativity showed that gravity also affects time. Massive objects, like planets, stars, and black holes, don't just bend space, they also warp and slow down the flow of time around them. This is known as gravitational time dilation. Imagine a clock placed near a massive object, like a black hole, and another identical clock far away in deep space, where gravity is much weaker. The clock near the black hole would tick more slowly than the one far away. If you could somehow survive near the edge of a black hole's event horizon, you might watch minutes tick by on your wristwatch. While eons pass in the universe outside, this is the ultimate time warp, a profound demonstration that time is not a fixed beat, but a malleable dimension. Profoundly influenced by the distribution of mass and energy in the cosmos, these revelations fundamentally changed our understanding. Time is not a river flowing universally at the same rate. It is more like a fluid, bending and stretching, accelerating and decelerating, intimately connected to the very structure of the universe. But even with relativity, a deeper mystery about time persists its arrow. Why does time only flow forward? Why do we remember the past but not the future? Why do broken cups never spontaneously reassemble themselves? And why does smoke always diffuse outwards, never magically gather back into a cigarette? This unidirectional flow of time is intrinsically linked to the concept of entropy that we discussed earlier, the relentless increase of disorder in the universe. The second law of thermodynamics states that the total entropy, or disorder, of an isolated system can only increase or stay the same. It never decreases. This fundamental law provides the universe with a clear arrow of time, from a state of lower entropy, more order, to higher entropy, more disorder. Time marches forward. The universe began in a state of incredibly low entropy at the Big Bang, a highly ordered, dense, cosmic egg. Since then, it has been constantly expanding and becoming more disordered, a relentless journey towards maximum entropy, a state often called the heat death of the universe. This cosmic arrow of time means that events are irreversible. The butter melts, the ice cube dissolves, the star burns out. These processes all increase the total disorder. Our experience of remembering the past but not the future is deeply tied to this arrow. The past is the ordered state that led to our present. The future is the yet-to-be disordered state. However, some physicists question whether this thermodynamic arrow is the only arrow of time. Is there a more fundamental quantum reason for time's direction? And what about the very beginning? If time began at the Big Bang, what was before the Big Bang? This question, as we gently explored earlier, leads to some of the most profound and speculative ideas in cosmology, such as the idea of time emerging from a timeless realm, or of cyclical universes. Consider the concept of a timeless universe. Some theories, particularly those attempting to unify general relativity with quantum mechanics like some approaches to quantum gravity, suggest that time, as we perceive it, might not be a fundamental aspect of reality at all, but an emergent phenomenon, just as temperature emerges from the average motion of countless atoms. Time might emerge from the quantum interactions of fundamental building blocks at a deeper level. In these models, the universe, at its most fundamental, might exist in a timeless state, a vast, complex mathematical structure where all moments exist simultaneously, and our perception of time's flow is merely a construct of our consciousness, a way for our minds to navigate this complex reality. This is a truly mind-bending thought, suggesting that the past, present, and future are all eternally now in some deeper sense. Then there's the intriguing idea of quantum time, in the realm of quantum mechanics. Unlike classical physics, time doesn't appear as a simple parameter that everything evolves against. Instead, it behaves in strange, often elusive ways. Some interpretations of quantum mechanics even suggest that time might be fundamentally discrete, like tiny, indivisible packets. Rather than a continuous flow, this would mean that time itself has a smallest unit, a fundamental tick of the cosmic clock, below which nothing can occur. And what if time could flow differently in other universes? In a level 2 multiverse, where the laws of physics themselves vary, it is a gentle possibility that other universes could have different temporal dimensions. Perhaps some have multiple time dimensions, allowing for richer, more complex histories. Or perhaps some have no discernible time dimension at all, existing in an eternal, static state. These are deeply speculative ideas, but they highlight how flexible and mysterious time truly is when viewed through the lens of cutting-edge physics. The quest to understand time is far from over. It remains one of the deepest, most beautiful puzzles. Whether it is a fundamental river that bends and flows, an emergent property of deeper quantum realities, or something that sprang into existence with the Big Bang. Time is inextricably linked to our experience of the cosmos and our place within it. So, as you rest in this moment, allow your mind to gently consider the nature of time. Feel its steady passage in your own breath, in the quiet rhythm of your body. Ponder its flexibility, its deep connection to space and gravity, and its mysterious arrow pointing ever forward. There is a profound peace in surrendering to its flow, in releasing the need to control its relentless march, and simply allowing yourself to be in the present moment. A fleeting yet precious point in the universe's grand, timeless story. Welcome, gentle spirit, to the quiet unfolding of our cosmic tale. Take another soft breath now, feeling the subtle presence of time, stretching and bending around you. We have journeyed through the mysteries of light and the fluid nature of time. Now, let us gently turn our attention to the very fabric upon which this grand cosmic drama unfolds: space itself, and its profound, often perplexing emptiness. Imagine space not as a mere void, a nothingness between things, but as an active participant, a vast, dynamic stage upon which stars are born, galaxies dance, and life emerges. For centuries, space was simply considered the absence of matter. The vast emptiness that separated celestial bodies, it was thought to be a static, unchanging container, but much like time, our understanding of space has been profoundly transformed by scientific inquiry. Early physicists, like Isaac Newton, envisioned space as an infinite, unmoving, and absolute framework. It was the unchanging stage on which all events occurred, a vast, fixed grid that simply was. This intuitive picture allowed for the elegant mathematics of classical mechanics, describing how objects moved within this grand container. However, once again, Albert Einstein's revolutionary insights reshaped our perspective. With his theories of relativity, Einstein revealed that space is not a passive backdrop, but is intimately intertwined with time, forming the unified entity we call space-time. And crucially, this space-time is not rigid and unyielding, It is dynamic and deformable. It can be stretched, warped, and curved by the presence of mass and energy. Imagine a bowling ball placed on a stretched rubber sheet. The bowling ball creates a dip or a curvature in the sheet. Now, if you roll a marble across the sheet, it will be drawn towards the bowling ball. Not because the bowling ball exerts a direct pull, but because the marble is simply following the curvature of the sheet caused by the bowling ball. In a profoundly analogous way, massive objects like stars and planets create dips in spacetime. What we perceive as gravity is not a mysterious force reaching out across space, but rather objects simply following the curves in spacetime created by mass and energy. The Earth orbits the Sun not because the Sun is pulling it with an invisible rope, but because the Sun's immense mass has curved the spacetime around it. And the Earth is simply following the shortest, most natural path within that curvature. This means that space is not empty in the way we might initially imagine. It is permeated by this gravitational field, this subtle, invisible curvature, and this curvature dictates the very paths of light and matter. When we look at gravitational lensing, for instance, we are observing light bending not because some unseen force is pushing it, but because the light itself is traveling along the curved paths of spacetime. Beyond this curvature, the vacuum of space. What we often think of as empty is, in fact, incredibly complex and vibrant at the quantum level in quantum mechanics. The idea of a truly empty vacuum is an illusion. Instead, the vacuum is a seething, effervescent sea of activity. This is due to a phenomenon known as quantum fluctuations. Imagine the vacuum as a vast ocean, even when it appears perfectly still on the surface. Beneath, it is teeming with activity. In the quantum vacuum, pairs of virtual particles and their corresponding antiparticles are constantly and spontaneously popping into existence, briefly existing for an infinitesimally small moment, and then annihilating each other, vanishing back into nothingness. These particles are virtual because they exist for such a short time that they cannot be directly observed or measured in the way real particles can. But their fleeting existence has measurable effects. These quantum fluctuations are not just theoretical curiosities. They have been experimentally verified. One famous example is the Casimir effect. If you place two uncharged, parallel metal plates very close together in a vacuum, a tiny attractive force emerges between them. This force arises because the space between the plates restricts the kinds of virtual particles that can pop into existence, while the space outside the plates does not. This imbalance creates a subtle pressure, pushing the plates together. It's a quiet testament to the reality of these quantum fluctuations in seemingly empty space. This means that space, even in its profound emptiness, is never truly empty. It is always alive with these quantum fluctuations, a shimmering, bubbling quantum foam. This has profound implications, suggesting that perhaps the very existence of matter, of everything we see around us, might emerge from this underlying quantum effervescence of the vacuum. Furthermore, space is not static. Our universe is expanding, and it has been expanding ever since the Big Bang. It's not that galaxies are moving through space, rather, space itself is stretching, carrying the galaxies along with it, like raisins embedded in a rising loaf of bread. The more space there is between two galaxies, the faster that space expands, carrying them further apart. This expansion is why light from distant galaxies is redshifted, as the very fabric of space stretches the light waves as they travel. And as we discussed earlier, this expansion is not just occurring, it is accelerating, driven by the mysterious dark energy that seems to permeate all of space. Dark energy is thought to be an intrinsic property of space itself, a subtle, repulsive force that pushes space apart. So, as more space comes into existence due to expansion, more dark energy comes into existence, leading to an even faster expansion. This cosmic feedback loop is reshaping the very long-term future of our universe. ensuring that distant galaxies will eventually vanish beyond our observable horizon. This omnipresent, accelerating dark energy suggests that even the seemingly empty vacuum of space is filled with a dynamic, fundamental energy field, a subtle pressure that governs the fate of the cosmos. It implies that space is not just a stage, but an active, energetic participant in the universe's evolution. So, when we contemplate space, we are not simply thinking about nothingness, we are thinking about a dynamic, deformable fabric, curved by mass, teeming with quantum fluctuations, and actively expanding under the influence of dark energy. It is a far more wondrous and complex entity than our everyday intuition might suggest. As you gently rest in this moment, allow your mind to quietly embrace this profound understanding of space. Imagine the invisible curves of gravity that shape the paths of planets and stars. Feel the subtle, constant dance of virtual particles popping in and out of existence, even in the empty air around you, and ponder the vast, accelerating expansion of the cosmos, carrying everything further and further apart. There is a deep, quiet peace in knowing that you are intricately connected to this dynamic, living space, a part of its silent, endless unfolding. Welcome, gentle consciousness, to the quiet hum of our cosmic story. Take a soft, calming breath, allowing yourself to drift gently into this moment. We've explored the dynamic nature of space, learning that it is far from empty, constantly stretching and bubbling with quantum possibilities. Now, let us turn our gaze to the most profound and perhaps most intimate connection we have with the cosmos, the concept of consciousness itself, and its place within this boundless universe. For much of human history, consciousness has been viewed as something separate, something residing solely within our minds. Distinct from the physical world, it's that inner light, that spark of awareness, that allows you to experience the warmth of the sun, the quiet beauty of a star-filled night, or the subtle comfort of these very words. But what if consciousness isn't just an isolated phenomenon confined within our brains, but is somehow deeply interwoven with the very fabric of the cosmos? Science, particularly neuroscience, has made incredible strides in understanding the brain, the intricate organ that supports our thoughts, emotions, and perceptions. We can map neural networks, observe electrical signals, and even identify regions associated with different conscious experiences. Yet, even with all these advancements, the fundamental question remains: how does a collection of billions of neurons, firing electrical impulses, give rise to the subjective experience of consciousness? This is often referred to as the hard problem of consciousness, a profound mystery that continues to baffle scientists and philosophers alike. It's a quiet puzzle. How does the objective, physical world of atoms and molecules transform into the subjective, inner world of feelings, perceptions, and self-awareness? We can describe the brain's mechanics, but we struggle to explain the experience of being conscious. This leads to fascinating, and often gently speculative, ideas that attempt to bridge the gap between the material brain and the phenomenon of consciousness. One such idea is emergentism, which suggests that consciousness is an emergent property of complex brain activity. Just as wetness emerges from the collective behavior of water molecules, even though no single water molecule is wet, so too might consciousness emerge from the incredibly intricate interactions of neurons in the brain. It's a system effect, a symphony played by billions of tiny components, giving rise to something far greater than the sum of its parts. Another compelling perspective, though perhaps more poetic, is panpsychism. This ancient idea, found in various forms across many cultures, gently suggests that consciousness, or at least proto-consciousness, is a fundamental, inherent property of the universe, present to some degree in all matter, even at the most basic levels. It's not that rocks or atoms are conscious in the way we are, but rather that they possess a rudimentary form of experience or awareness. a tiny spark of inner life. In this view, our complex human consciousness is not something entirely new, but a highly evolved and integrated form of this fundamental, pervasive awareness that permeates the cosmos. Imagine every particle, every field, every subtle vibration in the universe carrying a tiny, infinitesimal whisper of experience. Our brains, then, would be incredibly sophisticated instruments for collecting, integrating, and amplifying these countless whispers into the rich, vibrant symphony of human consciousness. It's a humbling thought, suggesting that we are not isolated islands of awareness, but rather highly sensitive receivers, tuning into a universe that is itself subtly aware. This idea resonates with the profound interconnectedness that modern physics often hints at. If quantum mechanics tells us that particles are interconnected and entangled across vast distances, and if space and time are fundamentally interwoven, perhaps consciousness too is part of this grand, unified fabric. Consider also the intriguing parallels between the structure of our brains and the structure of the cosmos. Our brains are vast networks of interconnected neurons, forming intricate patterns that give rise to thought. The universe, too, on its grandest scales, forms a cosmic web of galaxies, connected by filaments of dark matter, resembling a vast neural network. Is this a mere coincidence? Or does it hint at a deeper, underlying organizational principle that spans all scales of existence? From the microscopic to the macroscopic, it's a question that gently invites contemplation, rather than demanding an immediate answer. Furthermore, if we consider the multiverse theories we explored, particularly the many worlds interpretation level 3, where every quantum possibility branches into its own universe, what does this imply for consciousness? If you are constantly branching into countless versions, experiencing every possible outcome, then your consciousness is not a single, linear thread, but an infinitely branching, multi-dimensional entity. Each decision, each thought, each moment creates new quantum selves, new streams of awareness, quietly exploring every conceivable reality. This vision expands not only the universe, but the very nature of self, suggesting a profound abundance of consciousness across countless realities. And what about consciousness beyond our own planet? Beyond our own biological form, as we discover more about exoplanets, those distant worlds orbiting other stars. The question of extraterrestrial life and intelligence becomes increasingly relevant. If life is a natural outcome of certain physical conditions, and if the universe is teeming with potentially habitable planets, then perhaps consciousness, in countless forms, is not unique to Earth. Imagine the myriad ways awareness might manifest across the cosmos, from subtle, collective intelligences spanning entire star systems, to forms of sentience utterly alien to our current understanding. The universe, in its boundless creativity, might be a vast canvas for an infinite variety of conscious experiences. Even the concept of time we discussed earlier can be intertwined with consciousness. If time is an emergent property, a construct our minds use to navigate reality, then perhaps in deeper, more fundamental realms, consciousness exists in a timeless state. Could our perception of past, present, and future be a particular way of experiencing a timeless whole? Like reading a story linear page by page? Even though the entire book exists simultaneously, it's a deeply philosophical question, one that invites a gentle letting go of our everyday assumptions. Ultimately, the position of consciousness in the universe remains one of the most beautiful and profound mysteries. Is it an accidental byproduct of complex matter? Is it a fundamental property of the cosmos? Is it an emergent symphony or a pervasive whisper? We do not have definitive answers, and perhaps that is part of its quiet beauty. The very act of pondering these questions, of allowing our minds to wander through these possibilities, is itself an expression of consciousness, a testament to our innate desire to understand our place in the grand cosmic scheme. As you conclude this segment of our journey, allow yourself to simply be with this profound mystery, Feel the awareness within you, that quiet, steady light that allows you to experience the world. Perhaps in this stillness, you might sense a subtle connection between your own consciousness and the boundless, unfolding awareness of the universe itself. There is deep peace in this interconnectedness, in knowing that you are not just in the universe, but perhaps in some profound way, you are the universe, experiencing itself. Welcome, gentle wanderer, to the final whispers of our cosmic journey together. Take a soft, tranquil breath, letting the vastness of the universe and the mysteries of your own consciousness settle within you. We have traveled far, from the gentle unraveling of ancient maps to the dizzying heights of multiverses, from the bending of time to the bustling quantum foam of space, and, finally, to the profound enigma of consciousness itself. Now, as our shared exploration draws to a close, let us gather these threads of wonder, not to tie them into a rigid conclusion, but to weave them into a tapestry of peaceful contemplation. We began our journey with the image of Edward Quinn's historical atlas, a testament to how human knowledge, like a flickering light, gently pushes back the clouds of ignorance. We saw how this metaphor extends beautifully to our understanding of the cosmos. For centuries, the universe was shrouded in a dense fog of unknowing. The stars were distant, unchanging points. The planets, wandering lights. Our place in this grand scheme was often seen as central, isolated, and small. But then, through the tireless work of countless curious minds, fueled by a gentle, unyielding desire to understand, the cosmic clouds began to part. The telescope, that humble extension of our vision, allowed us to peer deeper, revealing distant suns, then vast island galaxies, and finally, the shimmering afterglow of creation itself, the cosmic microwave background radiation, an ancient whisper from the universe's infancy. We learned that our Milky Way is just one among trillions, and that our cosmic home is a tiny, precious island in an unimaginably vast ocean of galaxies. The universe, we discovered, is far, far bigger than we ever dared to imagine. Yet, this unveiling of distance only opened the door to new, more subtle mysteries. We learned that the universe isn't static, it's expanding, stretching the very fabric of space and time, and this expansion is accelerating, driven by the elusive dark energy, a pervasive force that will eventually carry distant galaxies beyond our view, plunging our future night sky into a profound, isolated darkness. This quiet realization reminds us that knowledge is not a finite destination, but an ongoing process, a dance between revelation and new enigma. Then, we gently stepped into the realm of the multiverse, a concept so grand it challenges our very intuition. From Max Tegmark's Level 1, we imagined infinite copies of our own universe, scattered across an infinite spatial expanse, each a subtle echo of our own existence, a mind-bending thought, perhaps, but one that suggests a boundless generosity in the cosmos. Realizing every possible permutation, we then ascended to Level 2, where the very laws of physics become variables. Here, eternal inflation births countless bubble universes, each crystallizing with its own unique set of fundamental constants, particle masses, and even dimensions. Our universe, with its exquisite fine-tuning for life, appears as a rare, fortunate pocket within this infinite ocean of possibilities. A statistical jewel in a cosmic lottery, we explored alternative Level 2 visions, like the cyclical cosmos, the Darwinian evolution of universes from black holes, and the fiery rebirth of ekpyrotic brains, each offering a poetic, profound answer to the question of cosmic origins and diversity. These theories, though still speculative, invite us to embrace a reality far more abundant than we might have previously conceived. Our journey then took a turn into the incredibly intimate, yet profoundly strange. World of quantum mechanics. We saw how particles exist in a superposition of possibilities, their reality only solidifying upon observation. This led us to the many worlds interpretation, a level 3 multiverse, where every quantum decision, every fleeting moment, causes the universe to branch into countless parallel realities. This concept suggests that there are infinitely many versions of you, living out every conceivable outcome, creating a vast, branching tree of your own consciousness across an almost incomprehensible tapestry of existence. It's a gentle reminder that reality, at its deepest level, is far more fluid and abundant than our everyday senses perceive. Finally, we reached level 4, the most abstract and perhaps most elegant concept that every conceivable mathematical structure corresponds to its own physical reality. Here, the universe is not just described by mathematics, it is mathematics. Our universe, with its specific laws, is simply one instance among an infinite collection of self-consistent mathematical possibilities. This ultimate level of the multiverse suggests a boundless universe of ideas, where everything that can be consistently thought can exist. It's a profound thought, suggesting an infinite wellspring of creativity at the very foundation of existence. Throughout this journey, we've held onto the idea that the universe, in all its complexity, is also a source of deep peace. The questions we've pondered about time, space, consciousness, and the very nature of reality are not meant to be answered definitively, but to be felt, to be explored with a sense of quiet wonder. The beauty often lies not in having all the answers, but in the profound act of asking the questions, in allowing our minds to stretch to meet the immensity of the cosmos. You are a part of this grand story. The atoms in your body were forged in the heart of ancient stars, and the light that reaches your eyes carries messages from billions of years ago. Your consciousness, that spark of awareness, allows you to contemplate these very mysteries, connecting you intimately to the vast, unfolding universe. As you prepare to drift into deeper relaxation, or perhaps into a gentle slumber, know that the cosmos holds endless wonders, endless questions, and endless peace. The clouds of mystery may never fully disperse, and perhaps that is precisely where their magic lies. For in the lingering fog, in the quiet unknown, there is always room for more discovery, more awe, and more profound contemplation. So, let your thoughts float now. Like distant stars in a tranquil night sky, release any lingering questions, any need for certainty. Just be with the immense, beautiful, and utterly mysterious cosmos that holds us all. This is not medical advice, nor is it a substitute for professional therapy or treatment. Its purpose is solely for relaxation and gentle contemplation.